This video is a demonstration about how to solve a couple of the problems in ChemActivity 2B, focused on atomic mass in particular. So looking at Model 4, what we see here is that we have this definition: the weighted average mass of an element takes into account the relative abundance of atoms in the sample with different masses. And as we saw in class with the examples of the golf balls and the ping pong balls, the mixture and what you have there is going to dictate what the average mass is. Now we want to be able to calculate it. And the equation is here. It's a little bit clunky, but the average mass can be calculated by taking the fractional abundance of isotope 1, of the first thing that's contributing, times the mass of that isotope, and then adding the fractional abundance of isotope 2 times its mass, plus the fractional abundance of isotope 3 times its mass, and if there's more isotopes, you keep going. Now this is not an easy equation to look at, so let's see how it actually applies. So in question 17 we see a table of the isotopic abundance of silicon. So silicon has 3 different isotopes, and we want to use the equation, it says model 3 there, but it should be model 4, to calculate the average atomic mass of silicon. So let's do one thing before we get started with the equation. We're given the abundance in a percentage, and I want to convert those to fractional abundances, because notice that in the average mass I need to use, or in the equation I need to use the fractional abundance. Okay, so what you can see now is that we have the fractional abundance for each of the 3 isotopes. Couple things. How did I get from percentage to fractional? I just divided each number by 100 to convert from a percentage to a fraction. The other thing to notice is that in both cases, the percent abundance adds up to 100, so these are all the isotopes that exist for silicon, and so their percentage should add up to 100. And the fractional abundance adds up to 1. So as long as you're dealing with all the isotopes, your fractional abundances should add up to 1. So we're going to use the equation. I didn't leave any space here on the document, so I'm just going to do it down below here to use the equation. Okay, so the average mass is going to be the fractional abundance of the first isotope, which is 0.92223, times the mass of the first isotope, which I find here. It's a big old long number, and here it is. So notice I've got the fractional abundance of the first isotope times its mass in atomic mass units. Now I'm going to add the abundance of the second isotope, 0.04685, times its mass, and I'm then going to add the third isotope and take its fractional abundance, 0.03092, times its atomic mass. So that's how we plug the numbers into the equation. Let's just pause at this moment and just see what we notice. First of all, we've already learned that the isotope that is present in the largest amount, just like if you have a lot of golf balls, it's going to skew the average mass towards the golf balls. So in this case, the isotope that we have in the greatest abundance, which is this one, the first one, it's 92%, that's going to be the largest contributor to the average mass. Let's see how this comes out. So if we, I'm going to do this in steps. So I'm going to do the first line, and then I'm going to add the second line and add the third line so you can see how this comes out. So here are the 3 values we end up with. So this number comes from this multiplication, the second number comes from the second line, and the third number comes from the third line. Let's stop and figure out our significant figures. So we multiplied in the first step, and our first value had 5 significant figures, and this one has way more than 5, but that means this is going to be limited to 5 sig figs. So that's going to mean that the 25.801 is significant and the rest of them are not. In the second step, we've got 4 sig figs multiplied by something with a lot more, so we're going to be limited to 4. So we are going to have to eliminate or underline as insignificant the 54878, so the 1.357 are significant. The same thing happens in the third line. 4 sig figs multiplied by something with a lot more, so we're going to be limited to 4. So we end up with a 0.9267 being significant. We're going to keep all those digits until we're done, but we're just going to keep track of what is significant and what is not. Again, now let's pause and ask what we're doing. We're calculating the average mass, and what we have here is this is the contribution to the average mass from the first isotope. This is the contribution from the second isotope. This is the contribution from the third isotope. And we can see right away that the contribution from the first isotope is going to be much, much larger, and that's because it is present in the largest abundance. So to get our final answer, we just have to add up these three numbers and keep track of our sig figs. Remember that here we know, now we're adding and subtracting, so we know 3 decimals here, we know 3 decimals here, we know 4 here, but we're going to be limited to the third decimal place because of the first two values. And this is what I get. So I would report 25.085 AMU. And that is the average mass of silicon using that equation above here. The average mass is the fractional abundance of the first isotope times its mass, etc. Let's answer the last two questions here. Compare your answer to the entry in the periodic table for silicon. So when I look that up, what I get is, let me go, it's 28.086 AMU. Now you might say, well, that's not exactly the same, but remember that when we calculate significant figures, the very last one has some uncertainty in it. So it's okay that this is a little bit different in that last digit from what we calculated. So we did a good job there. Question C, does any individual atom of silicon have this mass? The answer to that is no. This is the average. Now we do have individual atoms that have this mass, or this mass, or this mass, but no individual atom has this mass. This is the weighted average of all the different types of isotopes in the sample. The second example I want to put on this video is the answer to question 20. So we're given that the atomic mass of boron is 10.81. One thing to recognize about that is the average mass. And if we weren't sure about that, the rest of the problem tips us off to that. So boron has two isotopes, boron 10, which has a mass of 10.01 AMU, and boron 11, which has a mass of 11.01 AMU. So what we can see is that these two isotopes somehow get weighted and averaged together to give this as our average mass. And we can see that this is closer to 11 AMU than it is to 10. So that tells me that probably boron 11 is more abundant than boron 10. But let's see if that's borne out, because the question asks us to figure out what is the percentage of each isotope in boron. So let's start by writing out our general equation. So here's that equation. Remember that the average mass is always the fractional abundance of the first isotope times its mass plus the fractional isotope of the second isotope times its mass. Now I don't know the fractional abundances because that's what the question is asking me for. So for right now I just put an X here and a Y here. But this is the mass of the first isotope, the mass of the second isotope. So we have a pretty standard problem in an algebra equation where we've got one equation and two unknowns. How do we calculate what X and Y are? So we must need to rely on another equation or another relationship in order to figure out what X and Y are. Now, we're told that boron has two isotopes. And the other thing we know is that the fractional abundance of all the isotopes for a given element need to add up to 1. So the other thing that we can say is that X plus Y must equal to 1. So whatever the fractional abundances are, if this is 0.5 and this is 0.5, they have to add up to 1. Or this is 0.2 and this is 0.8, they have to add up to 1. So if X plus Y equals 1, we can do a little bit of rearranging to say that X is also equal to 1 minus Y. So I've subtracted Y from both sides. So now that I know what X is, what I can do is my little algebra trick here, and I can take this and substitute it in for X. So let me do that below. Okay, so what I've done here is I put in the average mass. I hadn't put it in here before, but I was given this in the problem, or I could have looked it up on the periodic table. And I've now, this is my fractional abundance for the first isotope and its mass, the fractional isotope for the second isotope and its mass. Now I have one equation and one unknown. This now becomes an algebra problem. So I'm going to multiply through and show you my next step. So what I get is the average mass is now equal to 10.01 AMU minus y times 10.01 plus y times 11.01. So now I can combine these two terms that have y in them. And I can also combine the two terms that don't have y in them. In other words, I can subtract 10.01 from both sides. So I'm going to do that. Let me just show you how I'm going to set that up. I'm going to say minus 10.01 AMU here, which of course is going to allow that to disappear, and 10.01 AMU here. So here's the next step in my problem solving. 10.81 minus 10.01 is 0.80 AMUs, and when I combined these two, I get y times 1 AMU. Now I just divide both sides by my 1 AMU. And what I get is that y equals 0.80. And it doesn't have any units. Notice that the units cancel out. So that's the fractional abundance of the second isotope. Remember up here we defined y as the fractional abundance of the second isotope. And remember we predicted early on that we probably were going to have more of boron 11 because the average mass was closer to 11 than it was to 10. And so 80% of the sample is boron 11. Now if 80% of the sample is boron 11, and remember that these two numbers have to add up to 1, that means that the other isotope is 0.2 in fractional abundance, or 20% abundance.